including us in this event. So it's very exciting to be part of this practice. And I'm working with Mohammed from MathWorks to guide you through one of the very exciting areas of chemistry, which is really combining a lot of different things to make predictions and generations of new molecules or materials um, to serve uh, real world applications. So this I have this presentation ready to give you. I don't know who our attendees are, but I will be brief in the slides, and I move to show you how things work in actual practice when you want to do the simulations or you want to do computations or using AI. So we work step by step toward generate, validate, and examine the performance of a new molecule, in this case, drug-like molecule, in a real-world scenario, which is in this case, again, drug discovery and how the drug is going to be having the kinetics in a patient's body. So we are, Muhammad and I, we are from MathWorks company. Let me go to the slide mode. We are from MathWorks. MathWorks is the builder of MATLAB and Simulink. MATLAB is our scripting platform, like the core platform, and then Simulink is more on the graphical side. You can go to this QR page and learn about the various solutions that people use our tools for from different industries, from automobile, aerospace, chemical, and pharmaceutical, so on and so forth. We have 100 plus tools that are built for certain application areas, from signal processing, image processing, optimizations, simulations and modeling, various kinds of machine learning, deep learning, app designer. It just makes a lot of things in terms of coding and computations easy. So we have online courses and we have introductory material for you to learn from. We are going to be using some of these tools in jointly with some of the tools from Python to do this practice together. I hope we can make it a pleasant experience, a learning experience, and I hope that you enjoy it as you do it as much as we mentor it and then we help you with it. Um, so why we are doing this practice together and why we are focusing on AI to do this. The idea is whenever whenever we pick a new method in our work, um, the first question I have to ask is, can I do it without that tool? Do I really need to use AI for this? And the answer is absolutely. The reason is, just look at this molecule. It is now, it's just a plane sitting on the plane, 2D, but this is actually a 3D structure, right? This is a molecule that can be represented as a graph that you see it, or as a text as you see in the bottom in a smiles format. Nevertheless, the whole idea is that if you are given a molecule like this, you should be able to measure or compute or predict some of the structural base physical chemical properties from just having this structure. Lipophilicity, solubility, polar surface area, permeability, things that in our case scenario, which is drug discovery, things that affect how this molecule is going to pass through different organs in the body and reach to wherever it's supposed to be reaching. So this part, the motivation to use AI is that going from this structure to here is extremely complicated to do it broadly, to do it multiple times with like thousands of databases. So if you want to increase the accuracy, you need to come up with the methods that lower the computation costs or the lab work that you are going to do every day to measure these. That's why we are always seeking to get high performance computing to use predictive models to get these numbers. Then the story doesn't end here. When you get these numbers, you are going to fit this in the real world scenario, which is here in this case, is pharmacokinetics, pharmacodynamics modeling, meaning that the data, the initial data, which is molecular structure, is going to be translated into this set of real numbers. And then these real numbers will be represented as coefficients to some ODE, ordinary differential equation systems, which is like basic chemical kinetics, as we learn in basic general chemistry or physical chemistry course, that represent how the body, how the drug influences the body, and how the body it reacts to the drug, which is pharmacokinetics and pharmacodynamics, which then at its core, it's basically modeling how a patient reacting to your molecular structure. Now, when you do, we do have tools in MATLAB to do all these steps. And this is what the idea of doing this practice together, to see how we can use those tools and how much they make it easy to do this. Now, after you do, let's say you get a molecule, you change it, you compute these properties, you send it to this modeling, PK/PD modeling, and then you get some result, right? This is like how your patient, let's say you have a diabetics patient, you have an oncology patient, you get this response through these modeling, which is very specifically designed. And we are not going to the details into this design of this model, but let's say you have the model, and then you send this drug into this workflow, and then you get this result, and you're not happy about it for different reasons. That dosage doesn't work. The patient's response is not as efficient as you were expecting. Now you need to go back and then do something to this structure, because everything starts from here. Now, the idea again for today is that how can we use generative AI to make such change, so that we close the loop and then do these iteratively, more time efficiently, and more effective, in a more effective way. So we will be using some cheminformatics, which is like really understanding this initial data that we have, given this text as the input file. Then we will use some predictive AI to predict these properties, and then we'll use some symbiology, which is MATLAB toolbox, to do PK/PD modeling, and then we use some generative AI at the end to see how we can generate a new molecular structure and see how it reacts. Now, the task that it's assigned to you is to go through this practice, analyze your data, get your understanding written in a paper, and then just do it together, and then stitch these individual codes together so that one code runs through it. Now, what I've done before, I gave you access to a package that have all the components in it, and then right now I'm going to move to that package and show you different components of this exercise. Your task in the hackathon, if you're practicing in the hackathon, is to just go one by one to those available examples that's already written. You don't have to do anything. You just run it. Need to set up your environment. You just run it and then understand it. Then move to the next component in this workflow. And at the end, the task is stitch them together, bandage them together. That is the common practice in these kind of workflows. You have different tools from MATLAB, from Python, from maybe C++. You should be able to stitch them together, to bandage them together, to build the workflow that you want. Now, now what we are going to be doing is in this package that you have, we have 8 steps, and I'm going to show you those steps. Step 1 is, if you are given a molecular structure, how can you visualize it? How can you bring it to MATLAB, visualize it, extract information from it, which is the core of cheminformatics. Now, if you are now given a database which has thousands of molecules in it, how do you extract data from that database and then be comfortable with that database, bring it to the whole database to MATLAB and visualize and manipulate your data? Then understand that data after you import it, after you visualize it. Can you categorize them? Can you partition them? Can you understand, okay, so what groups they are? Can you group them in different ways? So on and so forth. Then we do similarity analysis. What does those groups mean? If you are grouping like a database to 4 different groups, can you look at each group and see how these molecules within that group are similar and how they are dissimilar, unlike other molecules in different subgroups? Then we move, this is like the first 4 steps, extremely important, understanding your data. If you don't understand your data, there is no guarantee that your AI methods will work, because at the core, you need to be able to provide a clean, good quality data, and then have some idea about the statistics of your data, so that you know what you're expecting about from the output of the AI. Otherwise, AI is a, like, if you see it as a black box, then it's going to just chew on your data and give you something that you cannot really interpret, because you don't know what your data is, how much you can expect actually to for AI to work on that data. Step 5, we move to predictive AI. We use a specific type of deep learning, which is like transformer-based learning, to look at substructures and functional groups. If a structure is given, can I predict if some part of that molecule is not clear to me? Can I predict that? Or if some part of the molecule is bothering me in that final result that I saw in the patient, as I showed you before, because that part of the molecule is toxic, then can I just replace that? And what does AI suggest me to do if I don't have the background? After that, we just say, okay, so I know what this molecule is. I know what the substructures are. Now, can I predict those physical chemical properties that I want to eventually send it to patients from AI, instead of measuring it in the lab or doing computations? Uh, After that, we practice generative AI to generate a new molecular structures based on the input that we provide. And then at the end, we look at a very simple pharmacokinetics model, which takes in all the information that we practiced before in these previous steps into a real case scenario. We will be holding office hours through the hackathon. So to help you to set up your computers, there are some things that you need to be able to do before you can actually run these things. So you need to have some Python installation on your device. You need to have some MATLAB installation on your device. Anywhere you go, anytime you want to do anything like that, there is some initial steps. Set up your environment. So we are here to help you to set up your environment, which helps you to really easily do without worrying about your systems and requirements. Just focus on the science, focus on the coding, and learn from it. So please reach out to us and make sure that you spend minimum time in setting up your data, setting up your requirements. Now with this, let me move quickly to the code. So the package that I sent you, you should have received a package that has these. You see my left hand side, it says, this is now I am in MATLAB, MATLAB environment. This is what you are going to be working in throughout the hackathon. We will be calling Python, but you don't directly work in Python. We will be bringing some PyTorch models into MATLAB, but you don't directly work with PyTorch. So all the work that you do is simply put together in this environment. So you are given all the code, all the data you need in this package that you should have received. If you haven't received the package, if you don't know how to unzip it, how to look at it, then please reach out to us and we help you to make sure that you have all the codes and database that you need. So you should have 8 subfolders in this practice. And if you go to, so this is the environment on the left hand side. I see my current folder. And if I go to my current folder, I see these things. So these are the first thing in each folder is that you need to be able to open is the live script, which is .mlx file. This is the file that you are seeing right now on my screen. This is a live editor environment in MATLAB that allows you to write like turn your codes into chapters, meaning you have a title, you have table of content, introduction, text, equations, pictures, and code to explain code blocks and make it easier for others to read and explain and understand your code. You can hide all these codes. You can do a lot of things with it. So in each folder, there is an MLX file that the first thing you do when you go to any of those folders, you double click on that in MATLAB environment or in your window browser. Double click, MATLAB will open. If MATLAB doesn't open, again, you reach out to us to make sure that you have the license, you have the MATLAB installed on your system, so on and so forth. So that's what you want to do. There are some Python dependencies. Sometimes you see Python here. Sometimes you see a CSV file, Excel file, that is your database, and other things. Sometimes you see some .m, which are the utility functions, support functions for this main code to be working. But nevertheless, MLX is your environment. Example 1, which exercise 1, is install and test RDKit. Now, RDKit is, if you go to Google, RDKit here, if I go here, RDKit is a cheminformatic toolbox, which is at its core is a C++ library, but wrapped in Python. So we will be calling Python to do our cheminformatics work. Again, you need to have Python installed on your system. You need to have RDKit installed. We'll use PyPy installation for RDKit. I will show you all these steps in my office hours, how to do those, but nevertheless, there are some installation. It's explained here already very, very easily. If you go to read this RDKit installation, you can follow the instruction and install them. The idea for this practice is just to make sure that you have already kit installed, meaning that you have access to cheminformatics functionalities, meaning you can just visualize your molecule, you can categorize your molecule, you can highlight your substructures, you can do similarity analysis on your database, so on and so forth. Now this particular example is looking at the SMILES database. So this is like a SMILES file format. If you don't know what the SMILES is, I think there should be a link up here. If you click on these hyperlinks, it takes you to a proper web page that you can learn about that topic. So we have a SMILES. This is the common data format that we'll be using in this practice. And then you should be able to visualize it. If you have, this is D-glucose. So this is the structure, and we are looking at a drug that has some substructures is glucose-like. You see this part of the molecule is similar to this part of the molecule. Now, I'm now looking at these molecules, so I see that they are similar, but what if you have thousands of these databases and you want to extract, like group together all the molecules that only have this part, because this is like an inhibitor for protein, SGLT2, let's say protein or that the natural ligand is glucose, but you want to build a drug to inhibit it. So the inhibitor must have some similarity with the original natural substrate, which is glucose in this case. So look here, we have that substrate. If you're screening thousands of data, how can you use AI, or how can you use cheminformatics at the first place to do this screening for you? So it groups all the molecules that are good nominee for your future work. So this kind of work is exercise one, just making your feet wet. You're just making sure that you are comfortable with the idea of extracting and manipulating data with molecular structures. Then we say, okay, so this part, we were just having one molecule input in MATLAB. What if we go to exercise 2, which is your second component, and then I go here to exercise 2, and then exercise 2 has a CSV file. This is the file database that you will be working. This is like Excel sheet. If I open it, you see that you have a SMILES in column C, molecular structure. You have log S solubility, log P lipophilicity. So there are about 10,000 molecular structures in it, and we are working because these log S, log P are very important component, the properties that's important for how the drugs for pharmacokinetics. So this is what we want to predict, actually, to fit into our symbiotic model that does pharmacokinetics dynamics on a patient. So the idea is, if you have if you are given a SMILES format for a molecule, can you predict log S and log P? What are log S and log P? How they are related to structural of the molecule? And can you predict it using AI instead of computing it or measuring in the lab, right? And then after that, when we are comfortable predicting it, the idea is, now what if I generate a new molecule based on the similarity of these molecules that I have, and then generate the molecule, and then the generated molecules will send into the predictive AI to predict log S and log P, and then send it to pharmacokinetics dynamics. I hope this workflow is clear what we are trying to do. So this is the database. Again, we go to exercise 2. Exercise 2 is the same as exercise 1, but in this case, instead of inputting the structure one by one, as you see here, instead of putting SMILES here, we are extracting smiles from the database, from the CSV file, and just picking one molecule, and then writing down its log S, log P, and then visualizing the molecule. So this is what we care about this database, is log S, log P, and smiles format. Then we move to exercise. How much time do I have?
You have enough time, Hossein.
Okay. Okay. So exercise, then we go to exercise 3. Exercise 3 again now. You see exercise 3, we have an MLX. This is slide script. Then you again click on the slide script, and then you'll have this file. Now I don't have much writing here. The idea is that, again, you look at this original, like a select CSV file, and you say, okay, so what is this database? Now you can come up, be creative and come up with different things. This is the way that I did. I set up this practice, but you can just, based on your data, based on what you want to do, you can choose to do different things with your data. Even for this particular exercise, if you have some ideas, new ways of doing it, please reach out. We can discuss it and see if it makes sense to do that way. So the idea here is that you have 10,000 molecules, right? We want to group these 10,000 molecules based on the values of column log P and log S. So we want to see, okay, so how are these molecules close together in terms of log S, log P, not in terms of structures. We're not looking at structures. We're just looking at column D and column E to see how this data, these numbers basically, can be grouped together. So if you do that, if you normalize the data, log S, log P, to 0 and between 0 and 1, and you threshold it around 0.5, half, then you can just color code different data points. Like this has like about 10,000 molecules. You give them color green, red, blue, and black, depending on where they are locating in the normalized value of log P, log S. So you can see here that the most of the molecules have high log S, but low log P. So green is this. So high log S, low log P. You see, it's 8,856 molecules. You see this number I'm pointing here? This is green. So most of your molecules actually have low log P, high log S. Now, why is this practice is important? Because imagine you know that you want a drug with high log P, right? But then you fit, this is the only database you have, and you want to use generative AI to generate you a molecule with high log P. But you see here, out of 10,000, about 9,000 of your molecules has low log P. So then do you think this is a good database to run to generate molecules with high log P? I don't know. It may not be a suitable database because there is not much high log P molecules in here. Now, the other question for you to think about is that, okay, so this red is high log P, high log S. Do I always need high lipophilicity, high solubility together? Or in other words, is all red molecules are the best molecules in this case? Or should you have a balance between solubility and lipophilicity? Solubility means if you put the medicine in your mouth, how easily it dissolves, which is very important, right? So presumably, I always look for high solubility, right? But then at the same time, high lipophilicity means what? Means that it dissolves in lipids easily, right? So dissolving lipids, lipophilicity means that it can pass through membranes, cellular membranes, much easier because cellular membranes have a lipid layer on it. So you want high lipophilicity so that your molecule can pass through. Now, The idea here is to think about the balance between these two values. Where do you want these two to be in terms of to get the response that from the patient through that complex pharmacodynamics ODE system, ordinary differential equation system? Because remember, the way that these numbers work will be non-linear. So it's not like you always increase log S and the patient responds more efficiently. So it's non-linear. A lot of components go into play, and then it's a complex system. So that's why every time you make a change in the molecular structure, you have to send it through and see the response of your patient in order to understand how your change is it a good change, or is it not not a very efficient change. So this kind of analysis helps you to do that. So I want you to stay on this exercise. When you're doing it, think about how you're analyzing the data and understand log S log P concept. So moving to the next exercise, number 4 is similarity. Now we know the numbers. Now, step 3, we were just looking at the log P, log S numbers. We're not looking at molecular structure. In exercise 4, we now move to in this database. Instead of looking at just these two numbers, we're looking at column C, which is the SMILES itself, and we want to know, okay, so if I grouped like these 10,000 molecules based on their values on like S like P in 4 groups, how similar molecules within each group are with respect to each other and with respect to other groups, right? We want to know, understand better the structure. So this is the exercise that you do. You call some functionalities of chemoinformatics, and you say, okay, so looking at log high log P, low log S, pick 2 random molecules and plot them and see how similar. So similarity has a score. So you can compare 2 molecules and then give it a score. Closer to 1, meaning they are more similar. Closer to 0 means they are not similar much. It quantifies how similar without you looking at it. Of course, if I look at these 2 molecules, I see that they are not very similar, right? But what if you don't look at it and run this database 10,000 molecules, and then this is the way that you quantify it. So this is 0.03, which is very close to 0, meaning that these 2 molecules are not similar. Similar, it's like this one. You look at this 2 is molecule 1, and you log high log P, low log S. Look at this structure. Even by looking at it, you see that they are similar. So the similarity score is 0.93. So it's very close to 1. So of course you know that these 2 molecules are quantified to be similar. Similarly here. So this allows you to do that similarity analysis. Now we move to component number 5, which is starting to do predictive AI. So number 5, if I can just go to it. Exercise 5 is look at the substructure, highlight some substructures, right? And then if I don't like the substructure, I can ask AI to give me an alternative and say, okay, so you know what? I think this part of the molecule is giving my patient a toxicity side effect. Now I want to replace it, but I don't know much about my options. Can you give me some options? And then the AI, what it gives you is you see this text, it gives you some alternatives. You see, these are the substructures within these commas here. When I'm moving my mouse, these are the substructures that AI is suggesting you replace this with. So this is actually comes from this paper. So Kimbert A is a 10 million these nice people took 10 million data points from PubChem, from public data, train it, 10 million SMILES structure. They trained it, and they made the trained model as PyTorch model available for free for people. So this is, I think it's very important for us to all know that if you want to really contribute to human health, to human knowledge, we need to be able to openly share the data that we generate, the data that we build, the models that we build. If you're writing a paper, consider attaching your codes, consider attaching, making your data available. MathWorks in general, if you do work with us, you would know that we also support very much the open science initiative, meaning that we really want all our codes, all our data be available. We put everything on GitHub. We make everything available for scientific community, engineering community to use. So this is an example of community contribution. So the reason this code here works is because we are calling that model. You see here, again, when you go to this folder, you see MLX. This is your working environment. But this, beyond that, you see some Python code. You see that there are multiple Python code. I think some Python codes that's calling these highlighted areas. Now, moving to the next exercise. The next exercise is now, the previous exercise predicts substructures within a structure. The next exercise is coming back to the actual business. We want to predict log P, log S. Okay, so here you see two math files. So MLX again is here, but in the exercise 6, you see two math files. Don't touch these. These are the imported model from PyTorch from that paper. So this is fine-tuned log P, fine-tuned log S models that you can just double click on it and see what's inside it, right? So you should be able to understand what is it that we are bringing from that paper from PyTorch. So spend a little time to understand these two math files and then see the logic behind it. I did not explain BERT. I did not explain BERT model transformers and basically language-based learning, deep learning. But SMILES, at its core, it's a language. So each atom is similar to a word in natural language, like English, and each molecule is a sentence. And then within, you have the symbols that connect. Those are chemical bonds. So nevertheless, this code now is using BERT through these two math files to predict log P for a given structure. So if you look here, if you get this SMILES, the true log P value from that database is this, and the predicted value is this one. So we have some error, but the model is able to predict to a reasonable magnitude the log P. You can do the similar thing for log S. Now moving to the next exercise, which is fun part, and that's generative AI. Now, the generative AI, using again another nice contribution from the community. If you show you this paper, neural scaling of deep chemical models. This is a model called ChemGPT. We are co-executing basically ChemGPT. Now, if you go to MATLAB again, in exercise 6, what I told you that in exercise 6, you see these two math files, which are basically the pre-trained model, right? In exercise 7, the interesting part of exercise 7 is that if you go there, you don't see those math files. So you still see math files, but those are still for predictive. For generative, we are co-executing Python within MATLAB, meaning that you are calling ChemGPT to generate a new molecule within Python. and then you're bringing that generated molecule into MATLAB. So again, when you are working with these big, giant workflows, you should be able to just call any resources. So at MathWorks, we don't say do everything in MATLAB. We say be smart, look, see what's available for you, then just bring them in MATLAB, and MATLAB makes it easier for you to process all those complicated bandaging and connecting these things together. So that is what we're practicing here. So generative AI, what it does is that it takes some input molecules, and you see it generates some molecule, predicts some molecules, and then it sends it to, again, the ChemBert. So ChemGPT here generates some molecules for you based on the input you give it, and then and then send it to predictive AI to predict the log S log P value. Okay, so that's what exercise number 7 is about. Now remember, generative AI for molecular structures is a new field. So if you run this, you see that the performance is not really maybe super useful. You can this particular model that you're calling is not very helpful. Now the question for you is that I'm just calling ChemGPT. Take your time, practice this code, but then think if you have other molecules. So just Google, search generative AI for SMILES molecules and see what you get. See if you can manipulate this code, this Python code, right? The Python code, you see, the Python code goes to a Hugging Face website. You see, it goes here, it then runs the model on 24,500 molecules, and then generates the SMILES for you. Oh, by the way, again, when you come to the office hour, I show you some changes that you need to do in terms of the location for log files, location for your output, so on and so forth in the database. So nevertheless, keep in mind that the performance of generative AI right now is not as high as predictive AI. So it's a hot topic. People still are working on it. And then because of that, you may, I think this is from a year or 2 years ago, so you may be able to find a better generative AI model to work with. Now, the last exercise 8, if I can just go to it, is actually the very fun part. So that is this SBPROJ, Symbiology project file. Now, this is the only folder that doesn't have MLX in it. So click on bioavailability 3, Symbiology project. If you click, now you need to have Symbiology installed. You see a very simple Symbiology model. The Symbiology model shows you how, when you put a medicine, if you design a new molecule, it has a certain log S, log P, right? You take that medicine, it dissolves in your mouth. The dissolution has solubility. You see this parameter here, solubility? It's in this reaction, solid to dissolved. When you want to dissolve your molecule, the reaction, this diagram here that you see modeling the reactions that the drug goes through to be passed from organ to organ. This first component is mouth. The second component is blood plasma, right? So the first thing is, if you admin your drug orally, then it has to dissolve, right? That this dissolution requires the solubility to be in a certain range. Then after that, you want that to be passed through membranes into blood, and that is where log P comes in. So if I click here, just quickly show you this. You see this drug log P? This drug log P shows you how much of this dissolved drug is going to be passed to plasma. Then this is the way that you set up your pharmacokinetics. This is graphical, so you can just drag and drop these components and connect them to each other, right? So then after that, you go to model analyzer and just click on this run, and then it shows you the model. Now this is the last part. So this is where you see the log-P log-S that you've been working on will be play a role into actual patient's response. So the idea for you for this practice, for this hackathon, is that go to where did I go? You go to all these components, 8 components. At the end, I want you to see, so each of these components are separate. Right now, each of them are separate. I want you to look and see if you can write one code that calls Camber, ChemGPT, predicts log-P, log-S, and then send it to Symbiology and do it over and over. Meaning, in other words, if I can go back to my original presentation, I want you to close this loop, right? I want you to do this in an automatic manner. Stitch all these codes, build one code, everything is there. You don't need to write any code. See if you're comfortable enough to write a code that does this automatically instead of going through chapter to chapter. That's ask number 1. Number 2 is make sure that you practice good reporting. Write down your understanding and explanation of the result. Discuss your result from each chapter. So at the end of this project, what you are turning in would be 2 things. Number one, a code that connects all these different components and runs in one piece. Number 2, a paper that explains things, explains some results. You can very nicely, what's good about MATLAB is that you can always save all your results, all your plots, and generate a very nice publishable plots and tables. So I want you to write a short paper, explain your result, explain your findings, suggest new things. If you want to replace a model like Camber, take Camber out, propose something else. Just explain justify your choice of pre-trained models. And then number 3, just enjoy it. I mean, I think it's very exciting time to be a chemist. It's exciting time to be able to do all these, use the power of AI to make our lives easier. And I hope you liked what you saw, and I hope that you have a successful event. So I stop here. I don't know how I'm going in terms of my time, but yeah.
Thank you very much, Dr. Hossein, for your very comprehensive and insightful presentation. This is definitely going to be very useful for the participants in track 2, and just like showing a real world scenario where you can just leverage AI in chemical innovation and drug discovery. And this just like provide us a deeper understanding of the future opportunities and possibilities in this field. And just like before we just like move to the Q&A session, I just like would like to remind the participants, if they have any questions, they can write them down, and then we can just like address these questions through the chat. Or if you want to speak, please raise your hand and we could just like allow you to ask your questions. Okay, I think we have multiple questions on the chat. Shall I start some questions, Dr. Hussein?
Yes, please. So.
All right. So just like one general question by Yasser Riza, is there like any LLMs for genome-wide association studies? So they wanted actually to modify in a way that they want to utilize this genome study. So they were asking if there are any LLMs that you are aware of.
Okay, I see. I don't know. I mean, this is particularly, I would say no, I don't know, but they might be. So I see a different question so from Yasir. But
Yeah, you
in
can
terms
select
of,
the questions
yeah,
that you want to answer.
yes, yes. So I don't, the answer is I don't know, but they they're most probably are, but I cannot recommend any specific ones. So Abir is asking, I have a problem regarding extracting a file in the MATLAB. I tried every method. Any advice in how to make it work? Yes, please come to one of our office hours and we share the screen, we look at what you're doing, and then we help you out. Extract, I don't know what exactly, what file you want to extract in MATLAB. So we need to look at it. After Yasir is asking, after identifying the lead compounds, do we need to still perform molecular dynamics, especially in a dynamic or cellular environment, to validate the findings? Absolutely. So this part, the model that we're using is pharmacokinetics. So we are only looking at log P log S, means that it shows you how the molecule dissolves and how it passes through the membrane. We are not doing molecular pharmacodynamics. So what you're asking is that part, how fast the drug attaches to a target protein, how it's detaches. Do we need to do molecular dynamics? Do we need to do molecular docking? Yes, but that is to do PK/PD. So for now, in this practice, we're only doing PK modeling. I want you to please reach out to us. We can help you with the setting up molecular dynamics. We have examples that you can set up molecular dynamics in MATLAB. Do that with the same smile. So do molecular dynamics in parallel with these predictive with these pharmacokinetics property prediction, and then I show you one example that actually has all the enzyme kinetics parts to it, or dynamics of the molecule, and how to add those results into a PKPD. The next question, Dr. Hossein, isn't exercise 3 and 4 are similar since both are grouping similar molecules? Exercise 3 is grouping. Exercise 4 is looking at similarities. You are correct. They are the same idea, yes, but the first one is not looking at the structures, it's just looking at two numbers and grouping molecules based on the two numbers regardless of their structures. Exercise 4 looks at each group that you made in exercise 3 and look how similar molecules are. So they are kind of different tastes of the same thing. Mohammed, yeah, you request the next question. You requested that I build a model to predict both log P and log S. No, I didn't want you to build a model. I want you to bring an existing model, PyTorch model in MATLAB, and then use that. Since log P can be computed using the RDKit toolkit and log S is obtained from Hummel experiments, would it be more effective to focus solely on predicting log S? Please. So the log P prediction with RDKit is looking at fingerprints, which may not be as efficient. So it's very approximate. The reason we are doing log P predictions using this database that you see is experimental values for log P. It all depends on the accuracy that you want. If you're happy with RDKit prediction, RDKit computations of log P, which looks at this breaking different segments of the molecule, then yes, you can also do that same thing with log S too. So you can focus on that. Of course, this is like, if you're proposing an alternative way to do this, I would say absolutely drop log P, just focus on log S in your practice if you're contributing to the exercise. In general, what I'm telling to everyone, you can pick your method. I just gave an example. You can follow my examples if you're not comfortable to make changes to it. and just deliver two things that they asked for. If you're comfortable, like Mohammed is asking, I don't like to do it like P, I just want to do like S, go for it. Just do like S, do like P differently, but write it down in your paper, absolutely. So Mohsen is asking, thanks, Dr. Hossein, from your evaluation, why GenAI is not able to produce higher performance? Well, if you look at if you read the paper, it's very complicated. And the reason why it's not performing as good relies on the way that the model is set up. So it's very deep, it's very involved. Just please read the paper. Hassan is asking, you requested that I build a model to predict. Oh, it's the same question I'm reading, I think. Thanks for the informative research. I want to know if this approach similar to inverse Q SAR. Define similar. I don't think it's quite similar to inverse Q SAR because we are not the way that we are using Gen AI in this case is very like black box. So it's not really a rational design. It's AI-based design. So in that sense, it's at its core, it's different. But if you know how to practice, like maybe if you have another way to do it with the rational way of redesigning your molecule based on your understanding on the structure, pick a molecule and say, you know what, there are lots of hydroxyl groups on this molecule. That's why we see higher log S. But if I can just reduce that or add the link of the linker of a molecule or change some add some benzene here and there, it brings up the lipophilicity. It brings down the log S so that I get that part. If you can do that and just combine it with Gen AI or just replace it by Gen AI and compare the two methods, that would be actually make a great paper. So why don't you just show us maybe what you have in mind? But that was my answer. I think that's the end of the questions.
Thank you very much, Dr. Hussein. I think we have one hand. We allow Mohammed to speak. So
yes, please.
Please, if you can unmute yourself. Mohammed?
Hello, Assalamu alaikum.
Yes, hello.
You hear me? Hello?
Yes. Yes, I can hear you.
Thanks for this valuable presentation. We really يعني got benefits from it. My question is about this log B and log S, and you answer it. It's good because we have we have a chemical expert with our team. They told us this B is calculated. We can get it from the log B. While the log S, it's the solubility. It's come from the experiment. This is why we focus our model or Barrett model to predicting this log X, but using log S and log B for getting where we are going to get a new drug or new compound. So just to confirm, thank you for this.
Absolutely. I like your suggestion too. It makes sense. And if you are contributing to the hackathon, please go with your method. Others are going to try predicting both, getting them both from prediction. And we can sit and then look at the results at the end and see how it performs. Thanks for the suggestions. Great idea.
The last one is the final of this track to get a new drug or with the similar capability of one of the 4 group which we were preferring to have.
Yes,
but the generated model we use in the GPT, sorry for interruption, the generation of the smiles maybe failed. Yeah, we have to validate it to get one succeeded, and then we go to show to predict the solubility and log S and get log B and to see where are his correct group or not, and just to confirm this we are in the right track.
Yes, exactly. That's what you will be practicing. Keep in mind, based on the strength of the generative models that are available, you may not get a very exciting suggestion from AI for your new design. So you may try different inputs, combine different inputs, combine different structures that have a specific substructures that you're interested in to get something useful. So it's the exercise number 7 is a little tricky. You need to be able to just give the Gen AI good input so that it gives you a good output. If you give the whole database, it's just going to give you a very low value outcome. Just try it and you will see. So hopefully you can get like a really good, useful drug candidate. But that is what you explained is exactly what we are going after.
Thanks a lot. Thanks a lot.
Of course.
All right. So I see. Okay, so thank you very much again, Dr. Hossein, for this enlightening talk. And I think now it's more clearer than any time before with going through the steps and everything. And hopefully the participants will be bringing really innovative solutions that can just be very innovative in a way that we push the boundaries of research in this area. So thank you again, Dr. Hossein.
Absolutely.
And
Thank
we'll
you.
look forward to see you here soon.
Thank you so much.
So with that, I think we will have another break before our next talk at 2. So so we will just be back at 2:10 to introduce our next speaker, which will be basically using Professor Yusing, in which he will be basically speaking about his recent developments from South Korea, Seoul University. So we'll be back at 2:10. So enjoy your break and wish you all a great day.
Thank you very much, everybody.
Thank you.